Okay, let's get started. Chapter 7. So we're into the sequence diagrams, right? So we talked a little bit about the sequence diagrams and how we have to develop them for positive, negative, and zero sequence. For each of the different possible ones we have to do that. So if it's just a standard load, it's no big deal, right? You just represent it as its impedance, and that exists in all different sequences that it shows up there, okay? So positive, negative, and zero sequence, you'll show the loads all configured as they exist. For transmission lines, again, you're going to have the same deal. One of the things about transmission lines, though, because of mutual coupling, zero sequence impedances can look quite a bit differently when you have mutual coupling. That's because magnetic fields, the way they interact, can greatly reduce the zero sequence current. And I think at the beginning of the semester I talked about a project that I was involved with Eversource over in Connecticut. They had a trip of the nuclear facility because somebody hadn't considered the mutual coupling effect, and they actually had higher fault current levels at the end of the line than at the beginning of the line. So it actually caused a missed operation, which ended up causing a plant trip. There was a problem at the plant, so they had to declare an unusual event. And I haven't checked recently, but the last I knew, the lawyers were involved, and forget about having any technical discussion at that point, because lawyers will try to pin you down to a specific location. So for generators, and we talked a little bit about this, but just to reiterate, so if we are generating electricity, we are trying to balance, we're trying to generate as much of a balanced system as possible. So we should only have power sources or energy supplies in our positive sequence diagram. Now you can say it's negative sequence if you do ACB rotation, but for the most part we'll just treat this as positive sequence and only have the power sources that show up there. So the only time you should see a voltage source is in the positive sequence diagram for a generator. All the other cases, you should never see a voltage source. Current flows will exist because you've interconnected you've interconnected the sequence diagrams to get current flow, all right? Now, one of the things that we highlighted here is we said that that's approximately XD double prime. Don't super duper worry about XD double prime. If we have a chance, we'll go back to chapter 7 and we'll discuss what those fault current values, how they changed based on the time. But the XD double prime, if you remember from the real world per unit example we put together, there were some XD double primes, some single primes, and no primes. And that's really just has to do with the time that's involved with when you're analyzing the faults. All right, so also just really quickly, this 3ZN, again, just to reiterate, that's whatever the ground impedance is for the generator, okay? So it's 3ZN because we have 3 times the zero sequence current flowing into the neutral. So you have the 3 as a result of the 3 separate symmetrical zero sequence currents flowing in the neutral, okay? So that's why it's very important when you're doing a fault analysis to know how the 3-phase system is connected to ground, because you cannot complete your sequence diagrams until you know what that value is. That's the only one that you absolutely have to know the grounding configuration, and hopefully by the end of the class you'll understand why it gets to be a big deal. Most of the generators I've worked on, I've actually never worked on an ungrounded generator. All the generators I've worked on have had some sort of ground connection in the neutral. So every generator I've worked on has been a Y connected, and it's either been solidly grounded, which I haven't worked on a ton of those, a few. Those are like the smaller 480 volt ones, like the CAT diesel engines you see around campus. Those would probably be solidly grounded. The low impedance grounded would be the next step up, which would be up to probably 150 or so MVA, where you're trying to reduce the ground fault current to a manageable level that will minimize the damage. And then the next one would be the high impedance ground, which is going to limit current to less than 10 amps. So if you have a bolted single line to ground fault, you'll have no more than 10 amps flowing through the neutral because you have such a high impedance. In any event, you replicate or show where that impedance is in the neutral, you show it with the 3Zn. Okay? So that's how you determine what that grounding connection is. Okay? Now, sequence diagram for transformers. What was our mantra? Have you said it 1,000 times so far? Right, so what flows in the primary flows in the secondary. So if you think about it from the perspective of a transformer, the transformer, if you want to have a transformer that actually operates, if it's energized, if I have a primary winding, and I'm only going to show one, with a current flow through here, I had better have the ability to flow current in the secondary winding. If that has no connection, right, how much current can flow if it's open circuited? None, so I has to be equal to 0. What does this has to be equal to? 0, because, again, what flows in the primary has to flow in the secondary, okay? So, very important, primary flow, secondary flow, because when I look at my, and I'll just give myself a little bit of room, I'm going to show the transformer connected as a Y here and as a Y here. Current flow in here has to be able to give me current flow in that winding. Not at the exact same level, right? But it has to be proportional to it, okay? So, we talked about positive and negative sequence. What are those systems in and of themselves? What type of systems are they? They're perfectly balanced systems. So, if these are positive or negative sequence current, how much current would be going to ground if I have a balanced system here? Okay? How much current is flowing through here if it's a perfectly balanced system? Right? The current flows in and out, right? Because this current can continue here, this one continues on, etc., etc., etc. So, if it's a Y or a delta and you're talking positive or negative sequence, I don't care how the transformer is connected to neutral or not. I couldn't care less because this is always going to be 0. Whether there is a connection or not to ground is irrelevant for positive or negative sequence connections. Okay? So if I have a Y here and a delta here, and this is positive sequence current, those currents can absolutely flow, can't they, in the primary and in the secondary. No problem whatsoever. Works super duper effectively well. No issues, okay? So positive and negative sequence, if you are showing a transformer diagram, all you do is look at the transformer impedance and you just put that in as in your sequence diagram. You don't even have to think about the ground connection. Just put in whatever the impedance is. You're all set. For 0 sequence, it's much, much more difficult because if this is 0 sequence current, IA0, IB0, and IC0, how much current can, what is the sum of the current at that neutral connection? It could equal 0 if there's no connection, right? If there's no connection to ground, doesn't it have to equal 0? Because these currents are all the same, aren't they? So if those currents all equal the same, Kirchhoff's current law, sum of the nodal current says that has to be equal to the sum of these 3, right? Plus IB0 plus IC0. So the neutral connection has to be the sum of all 3 of those. If there is no path to ground because it's an open circuit, then you have no 0 sequence current. Stand back for a second. If there's no path to ground, you have no path for 0 sequence current. If I have my Y here, and I have a dead short circuit to ground, how much current flows through here? A little? A lot? A lot? Everybody agree with a lot? How about none? How do I complete the path? I have to go from, remember this is a power supply, right? I have to go from the plus to the minus. How do the electrons get to the minus? It's an open circuit, isn't it? The only time they have a path is when there is a connection to ground on the neutral, and then they can flow to the negative terminal of my power supply. So if I have an ungrounded system and I have a ground fault, I actually don't have a fault, right? I just have a connection to ground. So that leads us to believe that if it's an ungrounded system and I have a ground, there's no current flow that's going to flow, right, to ground. The voltages might be high, but the currents are going to be non-existent. So when I look at the case where I have a Y connection here, if there is no ground here, right, you know that no zero sequence current is going to be going into that transformer, regardless of how the secondary is connected. All right? Let's put a grounded Y on here. Can I get the 3 I zeros to flow here? Do I have a path to ground, and Kirchhoff's current law says the sum of the currents into the node equal the sum of the currents out of the node? So can I get zero sequence current to flow in that secondary side? A lot of no's. Why can't I? Don't you have a connection to ground? Well, keep in mind, right? This secondary transformer looks like this, right? So now I have a ground here. What if I have a ground connection here? Do I have the ability for zero sequence current to flow there? Will zero sequence current flow here? You will get zero sequence current flow, but how is that implicated, or how does that impacted with this guy? Because I am going to get some current to flow on this side, but I can't get any zero sequence current to flow on this side, can I? So from the perspective of zero sequence current, this one right here says no way. No zero sequence current can go on the primary side, because what's our mantra again? Flows in the primary, flows in the secondary. This says in the primary side, I0 has to be equal to 0. What does that say in the secondary side? I0 has to be equal to 0. Okay? So when you have a zero sequence diagram or zero sequence network, you have to look at it in terms of, can I have zero sequence current flowing in the primary or in the secondary? So that has been so important. We do something called transformer sequence diagrams. And the case we just talked about, which I just switched primary and secondary, doesn't matter. You can see that in this case, I could have zero sequence current flowing, but it does not flow through the transformer, does it? It doesn't flow through the transformer. It stops right here. So it's not allowed to pass. So zero sequence current can't flow through the transformer. Only positive and negative sequence current can, which would feed the fault, but not zero sequence. So the reason why I'm saying this, or putting this into perspective, is the fault currents are going to be determined based on how much current you have from the positive, negative, and zero sequence diagrams. This tells me right here, I'm not going to get any contributions from the zero sequence diagram. Okay? Does that make sense? These things get a little bit wonky, but they're very important to understand zero sequence connections and how they flow.
Is that the same on the right or the same on the left? Just showing how the
Yes, but I just switched primary and secondary.
No, I just mean in this diagram on the left-hand side, there's all how the windings are grounded.
all the way over here. Yeah, that just shows a single line representation. This is the actual three-phase representation. And this is how we actually show it in the zero sequence. So this is single phase if you wanted to append, three-phase, and this is the zero sequence representation. Susan.
Well, my question is why would you not just ground everything so you could have?
Why not ground everything? Because if you ground everything, and that's a good idea, but if you ground everything, remember, we're trying to limit ground fault currents to very low levels. So if I use grounded Y all the time, grounded Y all the time, then to coordinate at the 345 level, I can actually see fault currents all the way down at the 120 volt level, essentially. So you don't always ground things because you can isolate ground systems, so I can look at just a specific area and I can say, well, the ground current is going to be limited in this area and it's not going to pass through. So oftentimes you're going to do something, we'll talk about that in a few minutes, where you actually isolate grounds on one side so you don't have to coordinate your elements. You just look at the transformer stops as long as we polarize on zero sequence current, right? So ground current, or more importantly, zero sequence current, is what we're actually looking at. Because again, no zero sequence current can flow from this side to this side. So if I'm monitoring the 3I0 over here, I can set a protective element to trip based on a certain pickup and a time value, and I don't even care what's going on in this one because the 3I0 does not pass through the transformer. So if I have a fault on this side, I'm going to see it. I would not see a 3I0 fault current on that side. I would see a phase value that's increased. So my phase A, B, and C currents would go higher, for example, but my zero sequence currents won't. They're not going to change at all. So essentially, let me make up a little more room. If I have this diagram here, oops, let's do that again, where this is grounded, and this is the secondary side of my transformer. If I have a ground over here, then there's no zero sequence current going into here. It does not pass through and go here because the transformers they're electrically decoupled, right? How do electrons go from one side of the transformer through the other? What's that? Yeah, they go through the magnetic field. So if I have this ground over here, that's not referenced to this ground in any way, shape, or form. So they are electrically isolated, so there's no zero sequence current. So this ground over here has nothing to do with anything. It doesn't even cause an increase in current. If you have the second ground, it would change things, but the first ground, it doesn't change things. So that's why in our diagrams, that's the representation. So looking at the ground connections is a pretty important thing. Questions on that?
So like in the Y delta configuration,
Yep.
you would just have an increase in your...
Well, let's wait till we get to Y delta. Let's do the first one, and then we'll go to the second, and then we'll progress slowly. We feel okay on that one? So no zero sequence current can flow, is essentially what we're saying. Yes, sir?
In that one, ABC on the secondary, the currents would increase on the lines, you said?
If I have a single line of ground fault on the secondary, you would need a ground someplace. So in this case, on the secondary side, there's no ground, so you don't have a fault. It just shows up as a ground. It doesn't actually show as a fault because we only have a single ground.
Okay, but you were saying that the secondary, the currents will increase what we were talking about, I guess we said.
If I have two grounds, right? So if I let me put this over here. If I have this configuration, right? And this is grounded. If I put a ground here, right, remember this is really a power supply, there's a voltage source providing energy. How do the electrons get back to this point? It can't, right? It's only when you have another ground, right now these are electrically connected to each other, then you can actually get a flow of electrons to go basically through that power supply and then back to return to that location. Okay? How about the next case, which is even more mind-blowing? All right, well, let's put a ground on both sides. And what does that mean? What's our mantra again? What flows in the primary has to flow in the secondary. So if I've got zero sequence current flow here, because I have a ground here, right? I'm going to get some zero sequence current here flowing because I've got this ground connection, right? And clearly, I can have current flowing through here. But what's interesting is that this one does not actually stop at the transformer, right? The zero sequence current just continues right on until you reach that ground connection. So electrically, how does that represent? It's just hanging up in the open until I put this ground. Once that ground gets put in, then I can actually add some sort of a connection between here because of that secondary ground. So the zero sequence diagram for a transformer does not allow these zero sequence elements to flow into the neutral until you actually have a ground. So this is a type of system that actually, even though it's grounded on both sides, it actually is dependent upon the grounding of the secondary system to actually allow zero sequence current. So if you look into distributed generation studies, you'll see a lot of companies trying to put grounded Y on both sides. But that actually doesn't change your effective grounding because you need to have a ground on the secondary side. So a project I did a couple years ago, I was talking to somebody, helping somebody out, and they didn't understand why it didn't ground it. But this is a design that actually doesn't buy you a ground. So the question or the comment was, why not put Y grounded everywhere? It actually isn't effectively grounded. And so effective grounding is getting more and more important because an effectively grounded system means that the impedances aren't so high so that if you get a fault, your unfaulted phase voltages don't spike up. Right? Because if I'm sitting here and I'm in Barrows, new Barrows that has a bunch of 120 volt outlets off of the three-phase system. If I have a fault someplace in Barrows, I don't want that 120 volt, which is phase and neutral, to spike to 200 volts, right? That would damage equipment. The switches couldn't necessarily handle it, yada, yada, yada. So the utilities are obligated to limit those over voltages on the unfaulted phases to reasonable levels. Otherwise, people could get injured, equipment could be damaged, et cetera, et cetera. So there's a really interesting discussion or topic called effective grounding. And if you take the follow-on relay class to this class, you'll actually, we'll talk more and more about effective grounding. By the way, as of yesterday, I think, I put the request out, the Power 3 class should have an online section. So I know there's been some conflicts with people, but if you are interested in getting your concentration or learning more about protection and whatnot, you may want to sign up for that class. So, and I was speaking to somebody in ECE, and they said it's been approved for an ECE tech elective for many, many years, but it's an official number, so I don't think we have to go back to the faculty. So it counts as an ECE tech elective. That doesn't matter to the EET students, but the EC, it's like an EET, we have an EET tech elective, which means you just can't take, any old random class. It actually has to be an approved class. So that is listed as an approved, so that counts in your curriculum, it'll count towards your graduation. If you didn't know that already, So that's why if you look at the diagram, and I'm going to erase a little bit here to help you make it more visible. That's the reason why we actually have no connection to ground, right? Zero sequence current just blows right through the transformer. This is not always a good thing. Now, if you take a look at a distribution level, like going to feed your house or a commercial neighborhood, they would go with three-phase grounded Y transformers because 100 kVA transformer is noise to 1247 line. What is that, 10 amps or something like that? It's minuscule. So you really can't coordinate ground faults separately from phase currents because the currents tend to be so low. But once you're talking at the 345 kV level and you get 200 MVA transformers, you've got 1,000 amps, 700 amps, big levels of currents. You don't want your grounds to be much more than, 5, 10% of that. So you actually would have protection set up completely differently. So on the distribution circuit, you want, usually, at least on the East Coast, we have multi-grounded systems. You have grounds everywhere. And you have Y grounded transformers, and it makes it easier to ground. But at the transmission level, you almost never see grounded Y transformers. I've actually personally never seen a grounded Y transformer, not once, not at the transmission level, okay? And that's the reason why, because we can't coordinate it. You cannot protect for ground. And operationally, whether the transformer is connected Y or delta does not matter to the transformer and does not matter to the system. It's just for ground fault current coordination. Now, you still will need to have a ground someplace else. So what does the utility system work on? So typically, if you are and this is a project that I've worked on recently, you have a generator here and a generator bus. You might have multiple generators at a site. You have one generator or generator step-up transformer for the units. This one right here would be delta, and it would be grounded, solidly grounded Y. Transformers can handle large levels of current. If you're going to go and this is at the 345 system, let's say. Then we have a bunch of lines. If we want to step this down to, let's say, 115, we need a transformer in here. Whoops. Most of the time to go from 345 to 115 would be an auto transformer. But if it was a regular transformer, you would have this to be delta Y solidly grounded. So you can see this entire system is grounded because of that transformer, right? Pardon?
How is that? It's grounded through the secondary back here.
No, it's grounded through the primary, right? The Y solidly grounded transformer, there's a ground there. So you have a reference path. Why is there zero sequence current flowing? We haven't exactly said why yet, but that is grounded. And that's the most common transformer you'll see. Oops, is delta grounded Y, solidly grounded Y. You do find some applications where you put a ground in an impedance in the ground, but again, that's usually because you're trying to limit ground current. So there's some benefits to that, but that's only in distribution circuits, and it's only because you're trying to meet some effective grounding criteria and voltage criteria. I've never seen it otherwise. That's the only time I've seen any grounds in there. Yes, sir.
If there was a fault on that delta side where the 115 transformer is, what would happen to that whole line between the two transformers?
Ah, excellent question. So if there's a fault at the 115 level to ground, because of this ground here,
No, I was talking on the delta side, not the Y side.
this is 345, right? This is 345. So you have a ground here.
Yep.
Because of the ground associated with this transformer, it provides a path to ground for that one. So you would have fault current. But I'm setting you up a little bit because we're moving on to number 3, which is the delta Y transformer, right? Delta, solidly grounded Y. What's our mantra again? Flows in the primary, has to flow in the secondary. So I will ask the question. These are all zero sequence currents. And is there a path to ground on the primary side? Let's just look on the path on the primary side. So if zero sequence current is allowed to flow in the primary because of our mantra, then there is a connection to ground here, so yes, it could flow. So now the next question is, can zero sequence current flow on the secondary side? A lot of no's. Anybody say yes? One yes. So the rest are no's.
Well, if you stick to a rule, it has to be yes.
If they what?
If you stick to our rule, it has to be yes.
Our rule is what flows on the primary has to flow on the secondary. But the question is, can zero sequence current flow in the delta? There's no ground. No, don't sum up. Susan, do you want to say why yes?
Well, based off the example you just talked about a second ago.
Yeah, I just said an example that says otherwise, but maybe I was confused. It's really cold out. I'm still wearing my coat.
The current can be there, but you're not
So you're saying the zero sequence current can flow in the delta?
Until you pull it down to the ground.
The ground is somewhere.
The answer is you don't need a ground and you can see zero sequence current flow.
On what, A, B, and C phases of the current?
This is I0, right? This is I0. This is I0, right? What does Kirchhoff's current law state? Sum of the current into the node equal to sum of the current out of the node? So I've got IA, so I got I0 equals IA plus I0, right? Into the current node equals current out of the node. So how much zero sequence current can be flowing through IA? Zero, right? Because those currents have the same magnitude and the same angle, this current that goes in here is the exact same magnitude as this current, which is the exact same magnitude as this current, which is the exact same magnitude as this one, and this one, and this one, and this one. What am I doing? I'm circulating inside that delta. So zero sequence current can absolutely flow in the delta. It never leaves the delta. It circulates inside the transformer. So that's why we can actually use this and say, well, we can have zero sequence current flowing. It can enter or exit the primary side, the Y grounded side, right? Because you can see here, current has to come in here or exit there. But on the delta winding, it just continues to circulate on and on and on and on and on. It never leaves. So why is this the perfect application? Because we said this is the dividing line for zero sequence current. If I have a fault on this side of the transformer, on the primary side here, I can look at zero sequence current and I can actually see no zero sequence current change over here. Now the phase currents will go higher, right? Because you actually have, like if I have a ground on this one, then clearly I'm going to be circulating there. And so whatever winding, let's say it's that winding, you can see that's going to pull more current through that winding. So that's going to change the voltages and the currents on those phases. But absolutely, 100%, I can have zero sequence current flowing in a delta because my mantra is true. What flows in the primary has to flow in the secondary. Zero sequence current is flowing in the primary and will also flow in the secondary because of the circulating current. That's a big one. That's a pretty important one because if you can understand this, you've got a leg up on just about anybody else who works in industry and understanding why a single line diagram is configured the way it is.
Does it work the same way if it was a delta primary and Y secondary?
It works exactly the same. It's just the opposite. So you can have zero sequence current flowing on the delta, on the secondary side, which would be the grounded side. So instead of having it this way, right, you would have this.
Because that's a lot more common in delta Y.
No, it isn't. Nope. Why would it be any more common? I just showed an example of an application where my generators are generating voltage at 13.8 kV, and it's delta on the low side, and it steps it up to the high side, grounded Y. But I didn't show, so where's my application here? So let's clean it up a little bit. So let's just do one generator here, a transformer. It's delta solidly grounded Y over here up to the 345 kV level, right? This is grounded, because the generators are, but there is a generator circuit breaker here, isn't there? I have to have a breaker there to remove the circuit. So what happens when that breaker is open? That could be an ungrounded system, right? So if I have another transformer here, this would be auxiliary power for the facility. Most of these set up are delta Y grounded. Anybody know why? Again, I want to have coordination for my zero sequence. So when this breaker is closed, right, this is its own network of zero sequence. No zero sequence current's going to flow through these transformers, right? So by putting a delta Y, I actually set it up so that I don't have to worry about it. So my auxiliary transformer, you see on the high voltage winding, right, is the delta, and the low voltage winding is solidly grounded Y. And if you were to go to the Walmarts of the world where they're pulling in big, 5 MVA, those might be delta Y transformers, delta on the 1247 side and Y on the 480 side, because they need to have a ground for electrical safety on their end. Plus, they might actually have some loads that aren't three-phase loads. Yeah, because they might have a lot of lighting. So a lot of lighting for parking lots and whatnot, those would be 277 volts. Try to get as high a voltage as possible, although now with LEDs, that's changing because you have so much more efficiency. But if you can reduce the size of the current, you can reduce the line losses, because you think about it going out in a parking lot. Anybody know what I'm talking about, the Walmart in Bangor? What is it, 1/10 of a mile? If you go all the way to the end of the parking lot to the main entrance, they got to light all that stuff up. So you got to run some pretty long conductors to get there. So if you're running an amp over a number 10, that's very different than running 20 amps over number 10 in terms of voltage drop. So delta Y is your friend. And you can switch and swap high side, low side, all you want. Okay? You aren't all impressed, but that's a really, really big deal. To get to know that and understand why and how you ground things, when you do a preliminary plant diagram or system diagram, why do you use delta Ys, why do you not use them, is a very important understanding. And you will come across them a lot. If you do a lot of distribution, maybe a little less, but any of the transmission level industrial facilities, almost every industrial facility I've worked at has always used delta Ys, again, to isolate the zero sequence networks between them. Questions?
It's something also like delta will give you balanced voltages, right?
Nope.
What? No?
Delta doesn't give you balanced voltages. If you load phase A and phase B more than phase C, you're going to get different currents and voltage drops. Just because I have a delta here, right? Whoops. If I have a delta, if I put a ton of load here, and this is open circuited, isn't the voltage going to be at looking across here going to be very different than looking across those two? Because of the lightly loaded, less voltage drops across the line. Make sense on that one? Y, grounded Y with a delta. If it's delta, ungrounded Y, well, all we do is we just break that connection. What about delta-delta? Can what's flowing in the primary flow in the secondary? Sure, it can. But can any zero sequence current leave? No. So if there's any zero sequence current flowing here because of some sort of imbalance in the transformer, it can circulate inside the transformer. So it never exits or enters the transformer, but it gets there because it's induced because of the unbalance of the transformer system. Yeah, so typically, well, actually, let's do that up. So if you look at 3-winding transformers, just because I'm trying to be complete, you'll actually see if you have a solid grounded Y or grounded Y to grounded Y transformers, you can have some problems with operations. So what you'll typically see is you'll put what's called a buried tertiary in there, which would be a stabilizing winding. And that basically shows you how, if you look at my zero sequence connection, you'll see that there, but you'll notice that this is an open winding, which makes the system more stable. So if you have a buried tertiary, it would typically be a delta. I did an auto transformer that had a buried delta tertiary 4 months ago, 5 months ago.
So it was delta primary, delta secondary, delta Y tertiary?
Nope. If you have delta, delta, you would not have anything. You would not have a 3-winding transformer.
It's only with YY.
It's only with YY. Yes,
I don't see any deltas ground changed in any of
Any what?
Delta's grounded in any of the examples?
Well, that's because this one's a little bit different, but if you notice here, it says, here's the reference bus, is right there. You'll notice that this connects here, right? So the neutral is shown high, but this right here is either open or 3ZN. So that actually shows the connection. It's actually onto this bus. That's the zero sequence bus. That's a neutral bus. That's our reference bus. Okay? And this is the last one I said, auto transformer with a buried tertiary. And I added that in there recently because I had to do one this summer. Just for giggles, if you want to take a look and you want to play around with symmetrical components, you actually can use this website, and I don't know if it's going to run through this application. It probably won't. Yeah, it will not run. But if you type in stephenblair.github.io/seek, you can actually drag each of these vectors here, and you can make the system unbalanced, and you can actually see how perfectly balanced system, you get positive sequence. Once you start to drag them to not be the same, you're going to get some negative and zero sequence elements that are shown, and they're all just doing the calculation for the symmetrical components matrix. So if you want to check some of your work, you can go ahead and do that. Want to do an example? Anybody? Somebody? All right, so here's an example. We have two grounded generators. Excuse me. And let's see, so let's go ahead and start marking. So two generators, they have a subtransient reactance of 0.15 J, they're both the same. They're tied to a common bus that has a delta Y transformer rated at blah, 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 and this is 0.097, right? Transmission line is 30 miles long and has an impedance of 5.43 plus J 22.5 ohms. We have a grounded Y transformer with an impedance of 0.074. It doesn't say anything about the ground impedance here, so we'll just assume that these are both 0. We would like to draw the positive sequence and negative sequence diagrams for this, okay? So, first thing we need to do is, are we on a consistent per unit base? Survey says, well, this generator here is 150. Oh, that's the transformer. The generator's at 50 MVA, so this is at 150, 50. This is at 50, and this transformer over here is at 225. Plus, this is in ohms, isn't it? So that tells me immediately that I have to do some correction. So let's pick S base equal to 50 MVA. And now we're going to use 13.8 kV for our V base, and we're going to do it on the low side of the transformer. Oops, show it sideways. So this is 13.8 kV. That's my V base. This one's over here is going to be 115 kV. And this one is going to be 230 kV just by doing our per unit calculations by doing the values. This is going to be J.15 and J.15, right? Because those are on the correct base. We don't have to do any corrections there. Over here, we have to do some corrections because this is at 0.97, but it's not on its correct base. So this is going to be 0.097 times, what is it again? Is it SB new over SB old, or SB old over SB new? SB new over SB old, right, is what it's going to be. So it's SB new over SB old. So SB new is 50 divided by 150, and I get those values. For my line, I've got 5.43 plus J 22.5. How do I convert this to per unit? divided by Z base, right? Which is 115K squared divided by 50. This one over here is 0.074 multiplied by SB new over SB old, 50 over 225. And I've done all my per unit corrections. So at this point, this is going to be XG1, XG2, XT1. We'll call this Z line 1, sorry. And then this one right here is XT2. We're just going to show those impedances sort of generically to make things easier. Let me buy myself a little more room. All right, so now we can draw our positive sequence diagram, right? So if I've got two generators. How do I represent the positive sequence diagram of a generator? With a power supply. One at an angle of 0. We'll just pick one at an angle of 0 per unit because we're not told otherwise. Then we're going to put the impedance here, right? This is XG1. I have two generators. I'm assuming they're operating at the same voltage. This is XG2. Let me see if I can move those down a little bit. How do I move it down? I can't move it down. Well, let me erase it, and then I'll draw it further away to give myself a little bit of room, and I'll draw it rotated. So here is one, here's the other, here is the power supply. This is XG1, XG2. Now I go to my transformer. This is XT1. I go to my line, ZL1. I go to my next transformer. This is XT2. And then I stop there. I have no information. This is the positive and negative sequence diagrams, right? There's no change in those. They're exactly the same because the positive and negative sequence impedances, we are assuming those are exactly the same. We're not giving any information, so we assume they're the same. Yes?
Negative wouldn't have the power supply voltages, would they?
Pardon?
I thought you said negative sequence. I thought only the voltage showed up in positive sequence.
That's correct, yep. So she's right because what I said was this is positive and negative sequence, but this has to be deleted for negative sequence. Right? Don't show the power supplies there. Very good. You just show the impedances connected to ground. So then we have these two power supplies, right? They connect to this common bus, and then this just is our regular system, and then we can actually look at fault analysis for the system. This is all looking at a whoops, why did that change? This is my reference bus, not 0. Okay? Now we're going to draw 0 sequence. So now we have to look at the connections. So the two generators, right, are connected solidly grounded. So we have XG1, XG2. Those are solidly grounded, right? Those are connected to a reference. Then we hit a transformer. Now we actually have to look at the transformer. It's delta and it's Y, and I'm assuming that that is a ground. Yeah, delta grounded Y transformer. Okay? So we have a delta grounded Y transformer. What that means is no current can enter or exit the delta side, so that's an open circuit. Coming up from our reference is XT1. Now we have Z of the line. XT2, is that correct? Because it's grounded Y, it just passes right through, right? It doesn't stop there. So if you want, you can actually show little connections to show there, and then we're at the transmission line. So this is we'll call this, let's say this is bus 1. This is bus 2. This is the other side of the transformer. This is bus 3, and this is bus 4. Those are just arbitrarily chosen based on the system that we have. So we now have the positive and negative sequence diagrams for the system. Great. What do we do with them? Well, we're going to calculate fault currents, right? And so the way to calculate fault currents, the easy way to do it is to build our Y buses. So remember from chapter 2, just go back and build Y buses and build them that way. Questions on that? Make sense? Don't make sense? Sure? Good, because it's your turn. Should look familiar to you, right? Same one, very good. So we built Y bus. We did per unit stuff, right? I don't know if we built Y bus for this particular system, but we did Y bus. So now I would like you to calculate what the positive, negative, and zero sequence Y buses are going to be for these 3 systems.
So
Or for this system, I should say, not 3 systems.
once we do everything, we gotta do A inverse times.
You don't have to do any A inverse. You're just drawing the diagrams. We're not doing anything with voltages and currents as of yet. We'll do that when we actually start to look at chapter 9, which is now once we have the network diagrams, we'll figure out how to solve for currents and voltages and then phase currents and phase voltages based on these diagrams. So this is just a startup, which is figuring out, all right, we want to be able to calculate voltages and current, but we have to figure out what the impedances are going to be seen by each of those components. And so all this work is to do, how do we actually come up with those diagrams? But hopefully more important or more practical is, how is a system connected? Why is it connected this way? So if you look closely on this one, right, you can see a transformer here. What did we say about having auxiliary power? Delta, solidly grounded Y. Just like what we talked about earlier, right? You've got 2 of them. You've got one here and one here, right? So we isolate zero sequence current in that case. Over here, though, it is a delta-delta. That's a bad thing. But it is what it is. Whoever designed the plant, built it, that's what they came up with. And they've got a protection issue there that we tried to help them with, but they didn't want to fix it. So the problem is, if this generator here is open, this breaker here is open, which supports this generator, right? Because you can see this generator is in fact grounded through I think it's a high impedance ground. I can't remember the exact impedance, so I don't remember what the ground fault current is. But it's grounded. If this breaker is open, then this entire system, which is a non-trivial distance, it's probably a few thousand feet of cable, is ungrounded. And because it's a hydro facility, what happens in the summertime? Low water, you shut stuff down, right? And you might shut it down for extended periods of time, or you're doing maintenance on it. So if you have a ground that occurs during an outage, you don't even know it. Guess when you find out? When you close back in. When you close the generator back in, and then you get a ground fault current, then you're like, oops, that was a mistake. That's a bad thing. And so the way to fix it, what I told them to do is, there are a set of potential transformers on here. And the original way they specified them is broken delta to broken delta, right? Which, can zero sequence current flow through here? No way, Jose. What I told them is to actually put grounded Y here, because if there's a ground on this system here, right, that is going to allow some zero sequence elements to flow, not a lot, but a little bit, and then that actually would go to a relay, and then you can actually monitor the zero sequence voltage, and then you can detect that there's an issue. This one almost bit me in the butt because when I was back in the day, the way you used to do it, you couldn't use this design because you couldn't calculate it. So the way that you used to do it is you had a grounded Y with something called a broken delta. Why would this work to detect zero sequence currents? We have the current flow, right? It circulates through. If I put a little resistor here and I monitor this voltage across that resistor, that voltage is going to be proportional to the amount of zero sequence current. So the moment I have a ground that's picked up on this side, I get a circulating current, which circulates through that resistor, which means I get a voltage. Booyah, I can trip. This is called a 59N function. Try challenging Leo with that and see if he knows that. So when I'm saying that is because I did a project in Houston, and I almost issued a design that had a big, big generator, 150 MVA generator. It had 8,000 amp bus coming out of it, and it went to one common bus, and then there was a GSU that was delta solidly grounded Y, and then over here was another transformer, which was delta, and I almost forgot to put that onto that bus. And that was, you know, that would have been very expensive. Oops. But I caught it in time. But that's how you used to do it. Now, don't even bother doing that. You just use the smart relays. You can actually calculate those. And I did a wind farm design maybe 9 months ago that actually has the same issue. So the wind farm actually has 3 collection circuits that go to a common bus. This is what steps up and goes to the utility. This is delta solidly grounded Y. When the generators are connected and closed in, they have transformers here that are Y. They actually have 3 winding transformers Y with 2 deltas on them. But whenever these are open, this entire system, which is quite massive, is ungrounded. And so the way that I designed that is there was a set of PTs here configured just like this. And so when we'd monitor that voltage and we would say, well, if it's above, I don't know, 10% or nominal, I think is what I specified it, you would go ahead and trip, but only when all 3 of these breakers are indicated as open. So remember when I was talking about how grounding is very difficult in understanding it? You can see how the zero sequence networks are important, but you start to trick yourself, wow, it is a grounded system because the generator is grounded. Well, what if the generator's not connected to the circuit because the breaker's open? You can set yourself up for failure. Yes, sir?
But that's what those are for, the smart label, Y to Y.
Yeah, so the relays themselves, right? If you go into a relay, what you needed to do back in the day was this design here. So let me redraw it.
And that's only useful for when the generators aren't connected, essentially.
Exactly. But back in the day, that's the only way you could do it because the relays didn't have the smarts, right? They were just either microprocessor-based relays or electromechanical relays where they just monitored quantities and issued trip commands or not. Now, you just take and you, again, all the new stuff that I've seen, unless you're stuck with an older, you know, sort of a brownfield, everything going into a relay is here because once you've got these quantities, you know the neutral, you've got all the symmetrical components, you can actually run this into your relay and you can run those through the A matrix and calculate whatever you want. So you don't worry about broken deltas. Back in the day, too, you had to do things with phase shifts. Now they have things called CT connection matrices that actually will do phase shifts for you. So you used to have to do delta Y connected CTs. If you went through a transformer that introduces a 30-degree phase shift, you had to introduce it opposite 30 degrees to make sure that they were in phase with each other when you're looking at a differential element. But now the relays can actually phase shift them themselves. Makes it super easy. So most of the one lines that you'll see today, they're all Y grounded, Y grounded. You don't even need to worry about all that stuff. The relay will do it, which is great for all those lazy P&C engineers. But us protection engineers who have to do all the settings, our work has gone up exponentially because we get to make the relay do all the calculations. So smiling, are you one of those? I say that lazy. That's not actually true. It's just it's better to actually do it that way because once you know all the phase voltages, the individual phase voltages, you just have more information available to you. But it just means more work in the relays themselves. So more programming, which means higher billing rates,
More jobs.
more hours, fancier cars and boats, bigger houses, longer ski trips. Anything else I'm missing? I'm not going to address that. That's not an appropriate thing. Could be, doing better things for charity. Helping out people who are less fortunate than ourselves, right? Providing a better life for your family. That does not necessarily mean your kids. That could be your upper family. That doesn't necessarily charity, but there's lots of opportunities. Hot tubs? Sure. All right, so when should this homework be due? How about Tuesday? Is that doable? So keep in mind, you have to go back to your per unit diagram, make sure everything's on a consistent per unit base, right? So if I was going to do the process,
You want that whole system done, right?
yep. So your per unit homework should have the common base. Step 2, ID the buses, which is kind of step 1 and step 2. Step 3, draw positive sequence with sources. So the generators are going to be your sources. Step 4, draw the negative sequence. Step 5, draw zero sequence looking at ground, right? That's the biggest thing. And step 6, build Y buses. There's also a lab that I posted this morning that you can take a look and see. We'll have lab next week. That lab is more complicated than this one, this homework assignment. But it'll probably take you a couple hours to get this homework problem done. So I wouldn't dally. Questions in chapter 8. Again, this is, like I said, probably the second most important topic if you're going to be working in the utility power industry at all. Understanding symmetrical components, zero sequence, negative sequence, but more importantly, understanding the grounding and how that impacts all these quantities. Super, 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 super important. Anything for me? All right, I will see you next week. Have a great weekend.